Okay, picking up where we left off. Let's get to it. I now will move on past the common values for alpha, which we said are 0.05 and alpha 0.01. Okay, so from here, we are going to do a probability problem. All right, we're going to create it from an inequality. So here is the same picture right here that we just drew. There it is. So the probability that our mysterious population mean is within these two boundaries in the unshaded area. The probability that our mysterious mu is in here is 1 minus alpha. So these boundaries, the negative z-score at the alpha over 2 level and the z-score at the alpha over 2 level, are the extremes of our inequality. What is this z-score in the middle? This is the z-score of the mystery population mean, mu. Remember, mu is just a number, like anything else. Mu is a number, and that number can be converted into a z-score. So the z-score of the population mean here is in the middle. The probability that the mystery means z-score is between the negative z and the positive z at the alpha over 2 level is 1 minus alpha. So central limit theorem, what did that teach us last unit? It taught us that the z-score using the central limit theorem is x bar minus mu divided by sigma over root n. Where am I getting this from? I am getting it from the central limit theorem. And so if you just replace z with what z is equal to, x bar minus mu over sigma over root n, keep in mind, what are we trying to solve for in the middle of this inequality? We're trying to solve for the mysterious population mean, mu. So I'm going to do some algebra right now to get mu by itself. Ready? Here's the algebra. Boop, boop, boop. There it is, dot, dot, dot. There's the algebra. And what you get is this wonderful looking inequality right here. X bar, let me use the cursor, x bar minus z-score at the alpha over 2 level times the sigma over root n. I'm going to put parentheses around that just so you understand it's times the sigma over root n, is less than mu. Mu is in the center of the inequality, which is less than x bar plus the z-score at the alpha over 2 level times sigma over root n equals 1 minus alpha. Ladies and gentlemen, I present to you the formula, or the confidence interval formula right here. There it is. Now, notice this looks like alphabet soup. It looks nasty. But notice if you break it down, it's just x bar minus this piece, and it's x bar plus this same piece. What is that piece called? The z-score times sigma over root n? That's called E, the maximum error of estimate. It's called the maximum error of estimate. For those of you who have been watching the news for some time, they often on the news will give polls. In a recent Quinnipiac survey, or a recent Quinnipiac poll, it is found that 42% of college students don't like homework. There was a 3% error in our study. What do they mean when they say there's a 3% margin of error in our study? They say margin of error. Well, that means that 42% they said could be off by as much as 3% in each direction. So let me go back to my video right here. So that 42% is in the center. And you could add 3%, and maybe the true mean is up there, the true proportion, I'm sorry, is up there, or subtract 3% from 42. So the true proportion of people who don't like homework could be anywhere from 39% all the way up to 45%. There's my interval. Okay, so what is the confidence part in a confidence interval? Let me talk about that for a second in terms of fishing. If I have a net that's this big and I scoop it in the water, I'll be somewhat confident that I can catch a fish, right? How can I be more confident that I catch a fish? Well, how about if I make my net bigger? Okay. If I make my net bigger, I'm going to be more confident that I'm going to scoop it in the water and catch a fish, right? My confidence level increases as I make the interval bigger. Here's the downside to that. If my interval is smaller, yes, I'm less confident that the true population mean is somewhere between my fingers, or the fish is going to be in there. I'm less confident, but where it can be is in a much smaller area. I have it narrowed down to a spot. If I increase my confidence level, okay, by making my net bigger, I'm more confident that I have trapped the true population mean somewhere within here, but it could be, the true population mean could be anywhere within this larger area, this larger value. So it's a give and take. But the more confident you want to be, the larger you make your interval. So a 95% confidence interval might be this big. A 99% confidence interval is this big. That's the basic premise right there. So let's finally get to some problems, some examples so you can do your homework. Okay, so there are 2 examples and then we'll be done with this piece of the lesson. So what I did was I copied the confidence interval. So it's x bar minus e and it's x bar plus e. So the problem says if sample IQ data yields that there's 50 people were sampled, n equals 50. The sample mean was 111.4. And we know from a previous study that sigma was 15.2. Find A, the maximum error of estimate if alpha is 0.05. B, 95% confidence interval. And C, a verbal statement as to what the heck this all means. So I summarized all the data right here. And here we go. It says find the maximum error of estimate if alpha is 0.05. Wait a minute. Let me go back in the notes here. What was the z-score that corresponds to alpha 0.05? Here it is right here. When alpha is 0.05, the z-score is 1.96. But there it is. Get used to that. Z-score that corresponds to alpha 1.0 or 0.05 is 1.96. So notice how I circled z equals 1.96. So the error estimate is just this part of the confidence interval formula. The z-score times sigma over root n. So replace z with 1.96, replace sigma with 15.2, replace the square root of n with the square root of 50, and you get 4.21. Boom. Now B is super duper easy. Why? Because a confidence interval is nothing more than x bar, let me use the cursor, is x bar minus e and x bar plus e. So to make my 95% confidence interval, I do 111.4 minus 4.21 less than mu, which is 111.4 plus 4.21. After all that Greek alphabet soup during the lesson, look how not bad this is, equals 0.95. And then you get an interval that goes from 107.19 up to 115.61, and you are done. I hear my daughter coming down the steps here. Hold on, let me do a quick video. Hi. Hi, everybody. I know. Yeah. Say bye. Bye-bye. Okay. So what does all this mean? If you see this interval, by the way, you're done with the problem. This is it. Make sure you write it as that inequality right there, equals 0.95 because it's a 95% confidence interval. The verbal for confidence intervals will always be the same. We are 95% confident that the true mean IQ lies between 107.19 and 115.61. And then this is important, the best point estimate of 111.4. What is that best point estimate? That comes from this definition. All right, it comes from this definition. The sample mean x bar is the best point estimate of the population mean mu. All right, so let me scroll back down to our problem. And you're done with that entire thing. Always give a verbal statement for every single confidence interval you give. Test number 4 is king of the -1 points. If on test number 4 you do all the work and you write me a confidence interval, but you forget the verbal, -1. All right, we'll talk about more -1s later. All right, so let's say this. Let's say you go to your boss and you say, hey, boss, I got the best piece of data right here, and I took a sample, and I am only off by 3% in each direction, possibly. And your boss goes, whoosh. Of course, your boss is not going to hit you, but he said, that's unacceptable. I only want your data to be off by as much as 1% in each direction. I want it to be very accurate in the results. What is the only way to increase, well, one of the only ways to increase our accuracy? Wait a second, let's go back up to the very beginning. All right, things that affect confidence intervals are sample size. The larger the sample size, the more accurate the estimate. So let's go back down to our notes right here. And if we want to determine the sample size necessary to produce results accurate to a desired degree of confidence, you take this error formula, maximum error of estimate formula, and you solve it for little n. Again, the algebra here, boop, 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 there's the algebra, and you get this formula right here, okay? The sample size is the z-score times sigma divided by the maximum error quantity squared. So last example, and we're done with this lesson. We wish to be 99% sure that a certain random sample of IQ scores yield a mean that is within 2 units of the true mean. How large should the sample be? And it says assume that sigma is 15. So when it says we want to be 99% sure, that means we want a 99% confidence level. And confidence levels and alpha levels are always complementary. So if you are 99% confident in your results, that means the alpha level is 0.01. Confidence level, alpha level always complements one another. What is the z-score that is associated with alpha 0.01? It is 2.575. There it is. Go back up in the notes. Pause this video and go back up if you need to. Okay, so the sigma is 15, and then it says we want to be within 2 units of the true mean, so E equals 2. Now it's a matter of just plug and chug. The z-score is 2.575. Sigma is 15. Error is 2. Do not double the error. I know it's 2 units in each direction, but do not double E. It's just 2. And then square the whole thing, and then you're going to get an answer. When you get an answer, notice I wrote my wavy equals. Make sure you round your answer up to the next whole number. Why do we always round up? Because if you round down, you want to be at least that confident. If you round down, you are not going to be at least that confident. You will be less than that confident. So when you're doing sample size questions, always take the answer or the decimal that you have and round it up. Mr. Cody, what if I get a whole number as an answer? Do I need to round that up? No, you do not. You get a whole number as an answer, just leave it. Only when you get a decimal, round that decimal up. We're done. That was the lesson. Work on the homework. The homework involves confidence interval questions, and it involves sample size questions. Please, though, if I give you an alpha level that is not 0.05 or 0.01, say this just as a quick end of the notes. What if I say the alpha level hypothetically? Let me draw something out here. Is 0.04. How do you find the z-score associated with that? Well, first you draw a picture of a normal curve, and then split 0.04 in half. So that means 0.02 is right here. And that means 0.02 is down here, which means that I have 0.48 from the center out to that point. 48 and 2 add up to 50. So I'm going to look up 0.4800 backwards on my z-table, which I'll do with you right now. If I look up 0.4800 backwards on my z-table, I find that 0.4798 is closest to it by just 1/10,000. So that's 2.0, what is that? 2.05. So then the z-score associated with this, the z-score at that level is 2.05. Understand that as you work on your homework tonight. If you have questions, please ask me. Bye, everybody.